class, we're going to finish up our notes from section 3.8. So we've seen what the derivative of e to a function is in the natural log of a function, but we've not yet seen how to do it. What if it was, instead of e to the sine x, what if it was 5 to the sine x and the log base 5 of the tangent or something like that? What if it was some other base other than e? So what we're going to do is just show you how these are similar to any function. So we're going to start out with this identity that if you have any function, that's the same thing as e to the natural log of that function, as long as this function itself produces positive outputs. Okay, remember, natural log can't take in 0 or negatives. As long as this produces positive, a positive function, if you will, where the outputs are always positive, then we can say that this is true. Alright, now a to the x, if a is just some standard base, the rules for that standard base for an exponential function is a positive number and it's not equal to 1. Okay, well, if you take a positive number and that positive number is raised to some variable power, then your output is always positive, and it's never 0 and it can't be negative. So this is always positive, so we can take the natural log of it. So this is true. Right? Remember the property of e and natural log, they're inverses. So anything that the natural log is doing to a to the x, e would then undo it, so they would wipe each other out. We're left with just a to the x. So this is a true identity. Now, how do I use that identity? I'm going to, instead of differentiating a to the x, I'm going to differentiate e to the natural log of a to the x. So there I've just replaced that in my derivative notation. There is the a to the x that we started with, and we replaced it with e to the natural log of a to the x. Now, a property of logarithms, remember, if I'm taking the natural log of something to a power, I can bring that power down in front of the natural log. That's the power rule for logarithms, and so this is the same thing as e to the x times natural log of a power, or the natural log of a times x power. And if you remember, we know the derivative for e to the c times x, where c is some constant, and that's just e to the power, the same power, times the derivative of that power. And the derivative of x times the natural log of a, that's a line. Right? Natural log of a is just some number, so this would be no different than e to the 5x, and the derivative would be e to the 5x times 5. So that's the natural log of a, where a is just some base. Then we just simplify ex times the natural log of a. That was just a to the x, so we replace it right back into there, and there's our derivative. The derivative of a to the x is a to the x, right? Similar to e to the x, the derivative was e to the x, but we have to multiply by the natural log of a. It's the chain rule, basically. We have to multiply by the natural log of a, which is the natural log of the base. All right, so what's the derivative of 5 to the x? It's 5 to the x times the natural log of 5. Okay, so there's this scaling factor that takes these exponentials and scales them. They're derivatives, they're slopes. They're a little bit more steep if the natural log of that number is bigger than 1, and they're a little less steep if that natural log of that number is less than 1. So, for instance, if this were 2 to the x, 2 to the x, natural log of 2, 1/2 to the x, 1/2 to the x, natural log of a half. Right? Natural log of a half is negative, so that means 1/2 to the x is going downhill, and it is, left to right. For instance, 2 to the x, like I said, 2 to the x is positive. Its slopes, are positive, but the natural log of 2, is less than 1. It's positive. It's between 0 and 1, but it's less than 1, which means that that's the natural log of 2's slopes are a little bit less steep than the natural log of 2 itself. The output is a little bit higher than the slopes would be. So what is that? How does this relate to a to the u, where u is some function instead of a to the x? Well, we get to just use the chain rule. Okay, notice the derivative of a base to a power. So any base, any positive base, to any power, where this can be a function, it can be a number, it can be a scalar function. It can be anything. What do? It's just a natural log, and then there's the function itself, so it does repeat. And then we chain on the derivative of the exponent. Alright, so let's do an example. The derivative with respect to x of 3 to the power of sine x, the sine function. The derivative is going to be right here, the natural log of the base, natural log of 3 times the original function itself, so 3 to the sine of x, and then times the derivative of the power. So the derivative of sine is cosine. Alright, so there's what we get. Now, this is something that I like to do with this. I'm going to group this and this together and leave that. So 3 to the sine x power. But I'm going to put the natural log of 3 and the cosine together. So I'm going to write it this way initially, cosine x, natural log of 3. But remember, that property of logarithms. If I have something being multiplied by a logarithm, I can take that thing right here, put it up on top of the input as a power. So this is the way I like to write these. But it's just my preference. You don't have to write it this way in your homework. I like to write it as 3 to the power times the natural log of 3 to the derivative of the power. So it's a to the u times the natural log of a to the u prime. There's that little dot in there, a little freckle. But that's the way I like to write this. And if you look at the original formula, that's exactly what happened. There's the u, that, and there's the u prime, natural log of a. The u prime could, by properties of logarithms, go on top of the a. So we end up with a to the u times the natural log of a to the u prime. Okay, so that's my personal preference. But again, you could have stopped right here. 3 to the sine x times cosine x natural log of 3, which is just the original derivative. Alright, likewise, we could do the same thing with any base logarithm. So log of any base of some input. Notice what I've done here is just the change of base property for logs. Alright, so the way this works is log base a of u, that's equal to the log base b of the original input divided by the log base b of the original base. Alright, and I just chose natural log just because we know the derivative of natural log. It's 1 over that thing, so right there it comes into play. So I just changed this to natural log u, natural log a. And the derivative then would be, notice I just pulled this apart, 1 over natural log a times natural log u. This is a constant again because a was a number, it was the original base, so it's just some positive number. I can pull it out and then take the derivative of the natural log of u, which we've already seen is u prime over u. Alright, so we end up with u prime times the natural log of a. Okay, so how do I find the derivative here? Log base 5, that's the ln that we need, the ln of 5. And then we would take the derivative of tangent 2x over top of tangent 2x. So this is going to be the natural log of 5 times the original function. So the original inner function, that is. This is u in here, whatever was in the original one, so tangent 2x. And then we're going to take the derivative of that tangent 2x and put it on top, so that would be secant squared 2x. And then the derivative of the 2x would be 2. I'm going to stick that here in the front. Okay, so we end up with 2 secant squared 2x divided by the natural log of 5 times 5 tangent 2x. Right now I can multiply top and bottom here by cosine squared 2x. Cosine squared 2x. Again, this is 1 over cosine squared. This is sine over cosine. So cosine squared would be the common denominator if you want to treat these as fractions within fractions. And then this would cancel completely, leaving you with just 1 or just 2 on the top. Alright, and remember this is, if you want to rewrite tangent 2x, remember that's the same thing as sine 2x. Sine 2x over cosine of 2x. Alright, so we would lose the cosine 2x and it would leave us with one of these. And we end up with 2 on the top, natural log of 5. Alright, and then we've got a sine 2x times a cosine 2x. Alright, and then this is 2 over the natural log of 5. And then 1 over sine 2x is cosecant 2x. And then 1 over cosine x is secant 2x. And this identity you may recognize it from its alternate form in terms of sine and cosine. 2 sine x cosine x. That's the same thing as the sine of 2x. Alright. It also works for the inverses of these. Right, this is the same thing as 1 over cosecant. This is the same thing as 1 over secant. And we end up with, this is the same thing as 1 over cosecant. So the same thing works if we reciprocate these. So this cosecant 2x, secant 2x times 2, that's the same thing as 4 cosecant 4x. Okay, notice this was 1x, 1x, 2x, it doubled when we consolidated. 2x, 2x, it doubles. We consolidate and we still have that natural log of 5 out front. So this is what our derivative of that thing would simplify to. So it's simplified a long ways, right? But again, you would get credit with me if you had used just this original form. That would have been fine, rather than using the cosine to cancel it out and all that stuff. But just know that it does simplify all the way down to just a single trig function with a scalar. Alright, lastly, logarithmic differentiation. So if I were to be taking the derivative of this thing, I would need a product rule. Overall, I would need a quotient rule. Within that quotient rule, I would need a product rule. And inside that product rule, I'd have a power rule. And right here, I would even have a chain rule with the 1/2, negative 1/2, the derivative. So it would be a very messy derivative. I could do it, I could take it, but it would be very messy. What logarithmic differentiation allows you to do is when you have these expressions that you're deriving, or differentiating, I should say, and you are you're going to have to do a lot of steps, and it's going to be messy. What you can do is take the natural log of both sides, and then you can use properties of natural logs to separate this. Remember, if we have multiplication inside a logarithm, we can write that as the addition of 2 logarithms. If we have division inside the logarithm, we can change that to subtraction. And then the powers, we can change that to multiplication. So we could end up with something that looks like this: the natural log of the first part plus the natural log of this second part with 1/2 down in front minus the natural log of the denominator. And that's not that bad. It doesn't look as bad, especially because of the plus and the minus. We don't have to use product rule and quotient rule anymore. Right now, we do have a little bit of a chain rule thing going on over here on the left-hand side, though. We have to be aware of that when we're taking the derivative. So the derivative on the left equals the derivative on the right. On the left, the derivative of the natural log of y is 1 over y, and then chain on the y prime. Now the derivative on the right, remember, all these are logarithms. So it's just that goes down to the bottom, and then on the top is the derivative of that thing. So x squared plus 1 on the top is 2x. X plus 3 goes down, the derivative of x is just 1. Right, and then the 1/2's out in front. And then derivative of x minus 1 is just 1, so 1 over x minus 1. And there's our derivative of the right-hand side. Now, we can't have this 1 over y there, so what do? we multiply the left and right by y. That gets rid of the y on the left side, the 1 over y on the left side. But it puts this extra y on the right side. Okay, notice right here I distributed the 2 through the denominator to get rid of the 1/2. Right? But remember, it's dy dx. This all has to be in terms of x. So what do I do to this y? I use the fact that all of this used to be y. So I'm going to replace that y with the original right-hand side, and there's my derivative. Right? Remembering this is multiplication right here between the two. There's my derivative. And it was much easier to take than having to do product rule within the quotient rule with the power rule within the product rule. Right? And the chain rule as well. So it makes it a little bit easier to come up with the derivative of these more complicated looking expressions.